残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
So.
Okay, we're back. Indefinite integrals, antiderivatives, round 2, calculus boogaloo. Let's do it. So example 30. Let's determine the indefinite integral of the quantity z squared plus 1 times the quantity 2z minus 5 dz. Oh no, we're using z's instead of x's. Is this going to change anything? No, not going to change anything at all. Z's, x's, it doesn't matter. They're just placeholders. They're variables. You could use smiley faces you want or detailed pictures of a train. It doesn't matter. They're just placeholders. Don't get freaked out. Same thing. So let's take this in a less convenient than is maybe possible way, just by expanding everything out. So the indefinite integral of z squared plus 1, that whole quantity, times the quantity 2z minus 5 dz, we'll just expand the integrand. This becomes the indefinite integral of 2z to the third minus 5z squared plus 2z minus 5 dz. So all that's going on here is a little bit of algebra. This is just algebra. Okay, I trust that you guys can expand a polynomial. I trust that you can expand two two-term polynomials multiplied together. Cool enough. So once we're here, all we're going to do is we're going to break this into bite-sized pieces. First off, we're going to use the sum and product. So sum and sum and difference, not sum and product. So sum and difference rule. Okay, so we take the indefinite integral of 2z to the third minus 5z squared plus 2z minus 5 dz, and we split it up. So we get the indefinite integral of 2z to the third dz minus the indefinite integral of 5z squared dz plus the indefinite integral of 2z dz minus the indefinite integral of 5 dz. Okay, cool. Split it up. Now we use the constant multiple rule. So constant multiple rule lets us take all these coefficients out. I pull that 2 out front, I pull that 5 out front, I pull that 2 out front, I pull that 5 out. Or in this case, I'm just going to leave the 5 there because the 5, it's not going to be hard. We can deal with it. What derives to 5? Maybe 5z? Yeah, absolutely. So next step, we just apply power rule. So we apply the power rule. So the indefinite integral of z to the third dz is 1 over 3 plus 1, z to the 3 plus 1. So this whole first chunk right here, this whole first chunk right there becomes 2 times 1/4 z to the 4th. Similarly, minus 5 times the indefinite integral of z squared dz becomes minus 5 times the quantity 1/3 z to the third. And so on and so on. We do all the rest of it using the power rule. And because the integral signs went away, these guys are no longer there. Those big S's are gone. The integral signs went away, so the plus c is here to stay. We're just going to leave it right there. Cool. Now all we do is run through with a little bit of algebraic manipulation and simplify our answer on down. So 2 times 1/4 is 1/2. Minus 5 times 1/3 is minus 5/3. 2 times 1/2 is 1. And everything else is done. So our final answer is 1/2 z to the fourth minus 5/3 z to the third plus 2z minus 5z plus c. And just taking a quick derivative to double check, it's pretty dang easy to see that you get this back. Yeah? Take a derivative right here. So we get 1/2 times 4z to the third, that's 2z to the third. Take a derivative right here, minus 5/3 times 3z squared, we'll get minus 5z squared. And so on and so on. You can double check that it works. We're set. Cool. Hopefully this is a good reminder of what we were doing last time. Let's jump into everything at once. Let's try it out. Okay, so like I mentioned previously, we can turn every single result in the class so far, pretty much every single result, into something about an indefinite integral. That is, indefinite integrals are all about antiderivatives, undoing a derivative. So if we know how to do a derivative, just reversing the direction, we know how to undo it. So for example, d dx of sine of a times x, where a is any real number, is just a times cosine of ax by the chain rule. So just getting rid of that dx, putting a plus c, and throwing an integral and a dx on the other side gives us a fact about integration. That is, just like I've got right over here, the indefinite integral of cosine of a times x dx is 1 over a sine of ax plus c. Here, I'm just taking this a and I'm moving it on over to the other side and turning it into a 1 over a instead. The form I first had it in here is still equivalent. And the rest of them are exactly the same. I won't read it out to you, but every single result we've had gives us a fact about indefinite integrals. Here's a table. We got another table right down here. These bad boys are in your note packets. They're all over the place. Just everything we did in all of the videos so far lead up to this in the sense that we can turn it all around. We just doubled our money's worth. We took everything we had and we got a new result. Every single one result we had became 2 results. This is a fantastic value, mathematically speaking. It's a great, great thing. And even better, these are super easy to use. Let's do a few examples. Okay, first example, example 31. Determine the indefinite integral of secant squared of 3x dx. This seems like it's going to be super hard. It's not. It will take us about 30 seconds. So we look, secant squared 3x. We check up here. Oh look, integral of secant squared ax dx right here is just 1 over a tangent of ax plus c. So the indefinite integral of secant squared of 3x dx is 1/3 tangent of 3x plus c. We just took those a's and put 3's in everywhere they appear. And bam, we're done. Next example. Okay, example 32. Determine the indefinite integral of cosine of x over 2 dx. So, same thing again. We're just going to take the things we already know about derivatives and we're going to turn them into things about antiderivatives. So, just conveniently summarized in the table, we got that cosine of ax dx, if we integrate that, we get 1 over a sine of ax plus c. So looking at what we have x over 2. We could write that as 1 half x dx, cosine of 1 half x dx. So the integral of that guy is just, well, 1 over 1 half sine of 1 half x plus c. Or if you want to look at it a little bit better, 1 over 1 half sine of x over 2 plus c. And just doing a little bit of basic arithmetic, we end up with 2 sine of x over 2 plus c. Bam, done. Another one down. Next example. Okay, example 33. Let's determine the indefinite integral of e to the minus 10t dt. Using the second table we got, the second figure, let's just once again turn something we know about derivatives into a fact about antiderivatives. So just checking it out, we can see that the indefinite integral of e to the ax dx is 1 over a e to the ax plus c. So, using number 7 as given in figure 2, we just replace that a with minus 10. And we end up with minus 1/10 e to the minus 10t plus c, where c is an arbitrary constant. Those are all of the functions that have e to the minus 10t as a derivative. Cool. Another one down. Let's do one more. Okay, example 35. Slightly more complicated. Let's have some fun with it. So here we're going to determine the indefinite integral of, and here's a slight bit of notation, dx over 16x squared plus 1. So this is really exactly the same thing as if I put, instead of putting the dx up there, we're just treating that dx like we would with any other fraction. This is exactly the same thing as if I just put a 1 up there and put the dx afterwards. Exactly the same thing. Doesn't matter whether you do that or what we started with, just dx over on the top of the fraction. Just saves you writing a 1 for no reason, you know? So we'll leave it like that right now. Easy enough. All we have to do is manipulate this guy until it's in a form given in either the first figure or the second figure. That is, until it looks like a result we already know about derivatives. So I see that I have dx over something times x squared plus 1. So if I look up at my chart here, I can see that I have something like, oh, let's see, what could we do? Maybe something like this, integral of a squared plus x squared dx, something like that might work. Let's see what we can do. Let's see if we can turn it into something of this form. So the idea here is that we'll take this integral right here, and I'm going to factor out a 1/16. I see that I have something next to that x squared, and I don't want anything next to it. So I factor out a 1/16, which really is just requiring that I pull a 16 out of both this term and that 1 over there. So when I pull a 16 out of 1, I get 1/16 left over. So I have 1/16 times the integral of dx over x squared plus 1/16. Now, all I have to do is notice that 1/16 is 1/4 squared. And bada bam, I got this guy. I have taken my original integral and I have turned it into something that is of the form I have up here, other than that constant out front. That constant out front, it's just going to stick around. It doesn't matter. We'll just leave it till the end and we'll be good to go. So dx, integral of dx over x squared plus 1/4 squared. This looks pretty much exactly like this guy. Integral of dx over a squared plus x squared. I've got my x squared and my a squared backwards, but it doesn't matter whether a squared plus x squared is down there or x squared plus a squared. You square something, it's non-negative. You add two things, it doesn't even matter what order you do it. And that doesn't even matter if it's non-negative or not, but just to point out, add two positive numbers, you definitely don't even need to think about whether or not it matters what order you do it in. It doesn't. So we can use this guy. This is it. So 1 over a, tangent inverse of x over a plus c. So we take this guy, We turn it into our new form down there. We leave that 1/16 hanging out, and then we notice that our a here is 1/4. So 1 over 1/4 is 4. Tangent inverse of x over 1 over 4, that's 4x. So I get 1/16 times 4 tangent inverse of 4x, and then once the integral went away, the c was here to stay. We got that plus c sitting there, it's just going to stay there. Doing a tiny bit of algebra, we end up with 1/4 tangent inverse of 4x plus c. And hey, wouldn't you know it, we're done. The only thing we had to do was this step right here. This step was pretty much the entire problem other than just looking at a table. This step, this line right here, this was just a tiny bit of algebra. We just factored out a 1/16. And that's all we had to do. A little bit of pre-processing to put it in the right form. Cool. Let's do another example. Okay, finishing it off, one more example. Let's see exactly what's going on. Let's challenge ourselves with one more. Example 34, we're going to determine the indefinite integral of 4 over the square root of 9 minus x squared dx. So, looking at what we got, I've got a number on top. I can always pull that out. I can just turn this into 4 times the integral of dx over the square root of 9 minus x squared. And I can see pretty easily that what I have is an integral, dx on top, square root of something minus x squared on the bottom. So I look up here and I see, hey, number 10, that's got a dx in the top, an integral of a square root of something minus x squared on the bottom. Cool. This is going to be easy. So we just check out 10 in figure 2 right here, and we get our answer. That is, just noticing that 9 is 3 squared, it's exactly in this form already. This guy is exactly what we have right up here. This up here is exactly what we got. All we have to do is notice that a is just 3 in this case. So we get 4 times sine inverse of x over a, which in this case is 3, and then we put that constant there, plus c. The integral went away, so the c is here to stay. And we got our final answer. Bada bam, we're done. We got it. The indefinite integral of 4 over the square root of 9 minus x squared dx is just 4 sine inverse of x over 3 plus c. All right, cool. These look super complicated. These look difficult to do. They're not. They're just exactly what we did before, but backwards. It's a little bit inconvenient to memorize all these things. I don't know why you would. Luckily, people have taken the time to already go through and look at what we already know, make us some nice references, showing us how to do this easily. And there you have it. EASY. Easy. We got it down. Cool.
Okay, look, Scully, I don't want to jump to any hasty conclusions, but on the strength of the evidence that we have here, I think that what we may be looking at is what appears to be a series of
calculus
like
problems.
On what do you base that?
Well, on the
integrals involved
and the
calculus on the page.
But as always, I'm very eager to hear your opinion.
Well, it's obviously not a
calculus.
Well, why not?
おめでとう